Переходим к следующему докладу. Докладчик Артур Франц, основатель проекта CAM. Артур.
So, thank you very much. I would like to present an approach, a top-down approach to AGI, systematic top-down approach, where you start out with a mathematical formulation of an intelligent agent, and continue to a practical implementation. Actually, so thinking about intelligence is hard. It's an extremely complex topic. And the science of intelligence, like is called cognitive psychology, right? And it includes a huge research field that correspond to various cognitive functions like perception, attention, mental imagery, knowledge representation, memory, storage, retrieval, problem solving, acquisition of expertise, reasoning, and so on and so forth. And it's impossible to know everything about these things. And the question arises how we shall ever make progress on that. So, nobody has figured out how this thing works. I guess or maybe it's just delayed reward or so. You have to click and wait. So let's start with a general definition, right? That seems like a good approach. What is general intelligence? Well, it turns out that many researchers actually agree on what it is about, roughly. So you could propose something like this. Intelligence measures an agent's ability to achieve goals in a wide range of environments, using insufficient knowledge and resources. So that's about it. How can we build an agent where you can give him a wide variety of tasks, and that he can solve it then. And so what he suggests here is a systematic top-down approach, how I already introduced. And maybe after that, some cognitive functions, like the ones I enlisted, will emerge. So I would like to spend a few slides to introduce you to Hutter's theory of universal intelligence. Maybe some of you know it already. It is essentially, if you're looking for a mathematical formula that expresses a generally intelligent agent, so to speak, the holy grail of AGI, it already exists for 20 years or so. Hutter has derived it, and I will present it to you in a bit. So you have the agent framework. The agent makes an action and receives from the environment an observation and a reward. An observation may be a picture or so, and the reward maybe he wins a game or scores something or so. And fundamentally, these are two Turing machines, two computers. The agent computes an action and receives from the responding machine a pair of reward and an observation. So what you hear is, well, the agent gets born, and now is time step k. You have discrete time steps, and previously it has seen observations and reward pairs. And now in the future, all sorts of things can happen. And what he does is consider all possible combinations of all possible futures. So some might appear more probable, others less probable. And well, the goal of the agent is to find a sequence of actions from K to M that will actually maximize the expected sum of future rewards. Well, if you have that, well, if rho of y extracts the rewards, then the value of an action is quite a simple expression. It's just the expected value given the probability of the future given the past and the action that you have taken. Well, that's all quite easy if you know P, which is the probability distribution describing how your future will be. If you know how the future will develop, of course you can choose actions that get you the rewards, and you get the maximal intelligent agent. This is simple formulation and gets you already the maximally intelligent agent possible. well, intelligence has a maximum, right? Because in every time step there is only one action that is optimal, or there in a finite set of actions there is an action that is the best one, and that will corresponds to maximal intelligence. So this is known as the AI mu model. Now the trouble with it is that you don't know P, of course, and now you can start and to pick your favorite model. You can, but the question is how to do that in general, so that you can predict all kinds of development of the environments. So the idea is just pick as a model something like 2 to the minus the Kolmogorov complexity of the future given the past. What does that mean? The Kolmogorov complexity is the shortest program that is able to compute the future, given your past, what you have already seen, and the actions that you might consider to take. So in essence is the future that is the most probable is the one that adds the least new information. So that has the least new content. So if you see me walking to the left, the least new content is that I continue walking to the left. Where you don't have to add so much new in order to compute, to predict. And it turns out this is up to a constant factor, what so-called Solomonoff induction does. It considers not only the shortest program that computes the future from the past, but considers all programs that that are needed to compute the future from the past, or you can compute both the pair past and future. And here it is, the big formula. This the AGI agent. So if you came here to this conference to find out, is there a big formula for AI? Here it is. You can study it. And, well, I mean, I was quite surprised to see that for the first time. And I cannot walk you through the details of it, but it can actually put in one line. And this is essentially this expected return with respect to the Solomonoff prior and maximized. Well, and it reaches maximal intelligence with respect to certain optimality criteria. And what's the general idea of it? Well, you have to find short explanations for your data. So you have the data coming into your mind, and in order to explain and predict how the future will develop, you have to compress it. And if you have a compressed representation, you can use it to predict. So the compression is not because you want to save memory, but because it is actually an appropriate representation to make predictions. And that enables you to make predictions, and if you can make predictions about future rewards, you can reap the rewards. So the bottom line is that data compression is key to AGI. Or it's also known as the minimum description length. But we not only need the minimum, we only need further ones. But not just the shortest, we need the short ones too. So we have that agent that shows maximal intelligence. Well, unfortunately, it's impractical. Yeah, that's the bad thing. It exists for 20 years. It's mathematical expression. But it's very, very general, but it's impractical and it's incomputable. And the idea for the top-down approach is actually to say, okay, the agent works in a very wide range of environments. Mathematically, it's the set of lower semi-computable semi-measures. And actually, it's way more general than we need for AGI. Well, we take many properties of the universe we live it for granted. For example, the properties that actually every object that we have is decomposable into properties. It has a shape, it has a color, it has a form, and this decomposability of objects into properties or various features is actually something special. It's mathematically not fully general. So you can introduce that assumption to make the universal AI agent less universal, but still general enough for AGI. So that's general reasoning. And you can use other assumptions, like the chronologicity, that the future does not influence the past usually. It's also an assumption, right? Doesn't hold for arbitrary probability distributions, right? You can assume that there is structure at all scales. That's a very important one. So you can zoom in everywhere and you see structure. You zoom out, you also see structure. And for arbitrary probability distributions or for arbitrary data strings, this is not necessarily the case. But for the world we live in, it is the case. So you can actually mathematically formulate what it means to have structure on all scales, using algorithmic information theory. You can actually express it. So, and that leads to the so-called renormalization techniques of IXE. And you also can exploit the locality of structure. Well, we don't have to travel to a different galaxy to find out that this is a straight yellow line. The regularity that we are looking for is not far away. The points that are correlated to each other are not far away to each other. So this is another property that's quite general. So let me introduce one first step that we have made is the using that there are properties actually. So if you have a data string, you want to find a decomposition into various its properties, we call features. Well, it's actually possible. You can derive a mathematical theory that does that. And how you do it is you have a data string, let's say zeros and ones, a sequence of them. And you find a pair of functions, one the inverse of the other functions that that is an autoencoder essentially, that maps it to a residual R, and that is able to reconstruct the sequence back again. Similarly to a deep belief network, for example, except that the functions don't have to be neural networks. They're general functions, computable functions, right? They can be neural networks, they don't have to be. So when you continue to do that, it's a stacked autoencoder, what you get. You have to search for those features. And what we could actually show that the information content, that's the Kolmogorov complexity again here, the shortest description of a data string, decomposes into the descriptions of those features. So it's like saying this object consists of a description of the color, of the shape, of the position in space, and so on. That's that kind of decomposition and an incompressible rest. And we could show that we can actually express the Kolmogorov complexity as the sum of this, of the information. And these decomposition like many decompositions in math or in computer science, allows for an acceleration of the compression process. So, and that way compression can be made much faster, and we can use it to get IXE running. And this is what we have actually done. So we have spent the last 2 years or so to develop an inductive programming system that searches in trees of Python operators. So it's in abstract syntax trees inside Python itself. So for example, a list of ones can be generated by multiplying here by A. And what it does, it searches for autoencoders, just like the theory of incremental compression suggests. So it doesn't have to find the full description of your data. It suffices to find a partial description that compresses the data at least a little bit. If it compresses a little bit, then it goes on and compresses it further and further and further. And it's also a search within hypertrees, so functions that you found that are useful can be reused within a single node. So it's a search within the space of hypertrees of programs. I cannot go into much detail with this. I can show you just the results. If it works. No. So what have we done here is, well, you can compress simple geometric figures that as you see. It can play tic-tac-toe without specifically programming it for it. So what you do is there you have a list of lists of chars, which are crosses or x's. And it compresses this list of lists and can predict what position you will get depending on the move you make. And then it uses, and we insert it into AGI, and AGI selects the appropriate action. So it can play tic-tac-toe. And we have to stress we haven't programmed into it what moves are or what does it all, and it doesn't know about the game. It's just compression and prediction and action selections. That all it is in all generality. And we have an instance of self-improvement too. What we have is a compression algorithm, essentially. And that's what you need to get AGI running. But AGI is a fully fledged intelligent agent. So it can solve problems, including those that you encounter during the development of the compression algorithm. Usually you encounter a problem, you think about it, try to find a solution, and then you hack it into it, and then it's hard-coded then, and then it's too specialized and narrow. It works in some cases, doesn't work in other cases. And it's all just, you don't want to do that. So what we did, we said, okay, our philosophy is not trying to use any heuristics. We use it to improve itself. We have just one test case. It's not generally working, but it's enough to demonstrate the ability.
3 minutes.
Mm-hmm. So, and the last thing is we have done it and asked ourselves, well, can we move beyond these toy problems, essentially? Let's apply it to practical data science. So another project that we have been working on for years is building a bot that makes automatic bets on horse racing. Well, it's a general data science task. So you have arrays of data, long arrays of speeds, jockey IDs, track, race distance, and essentially, etc. And the task is to build factors that predict the winning probability of each horse. Right? It's a data science task. You can do it by hand. You can train some models on it. Well, we asked ourselves, well, can we use William, or AGI, so to speak, a compression algorithm, induction system, to help us out with it? Well, it turns out it's possible. One of the main things that you want to find out is how to combine those factors in such a way that they carry predictive value about the winning probability of a participant. And well, you can try various combinations with various constraints, but you can also use such an induction system that to try out automatically various combinations. And if it has found a combination, it transfers the speed to some residual speed. Essentially it subtracts some value from the speed array. So, for example, they run for different obstacles, they run faster or slower. And you can normalize the speed this way and have, and the task is just to compress. If the description length of this residual speed is smaller than the original one, then you have already compressed a little bit. And you can do that further. He goes on and grows the trees incrementally. Here he finds some other factor, and he compresses even more. So he grows the trees more and more incrementally, and in the direction where he actually achieves compression. And the more compression he achieves, the more well, this means here that the compression means the description length of the residual gets smaller. And that means essentially the error is smaller. It's in data science terms the minimization of logarithmic loss. That's what essentially it does. In other cases, it actually maximizes the likelihood, logarithmic likelihood. It can also be mapped to compression. Well, Alexei Potapov has a whole monograph on the role of minimum description length principle in data science and machine learning. So, well, does it work now? Not anymore. And another thing he does, he can do regression, for example. You multiply a factor with with a weight and another factor with a weight, and then keep adding those factors. And he can find those weights by using his internal algorithms. There is nothing specifically programmed to do this regression. Well, of course, it's nothing surprising. Everybody can do linear regression, right? But the thing is, he can do regression and at the same time build those factors here. He does it all in parallel. All sorts of programs that he can find, he uses he looks for in parallel. And yeah, well, and it helps us making profits. So I come to the end of the talk. So the approach to the AGI is to branch from abstract theory to a practical data science application. We have done sort of one sprint of doing this essentially. And because we actually want to have both. We want a solid mathematical approach to general AI, and we also want to work it to work in practice. So what we do is start with a definition, make a precise formulation, and then introduce assumptions to derive efficiently computable versions, and then implement algorithms according to those mathematical descriptions. And the general philosophy may be, well, up to now, before the AGI attempts, people have been trying to look at the task space of various tasks that we might solve and try an algorithm and try to solve some complex tasks. But maybe this is not the best approach. Because if you have a narrow algorithm, it can solve complex problems, but it cannot solve other complex problems or other simple problems for that respect. So maybe we should, in order to approach general AI, we should build algorithms that can fill the cup from the bottom up. We can start with a system that solves a wide range of simple problems that you have seen. Like we have this regression with big data of horse racing. Then we have the tic-tac-toe playing, and then we have image perception examples, self-improvement examples, all with the same system. So instead of using narrow AI, where you have to start from scratch every time you get the different tasks, maybe the picture should be something like this. You start and build a general system that is general from the very beginning. It just solves simple tasks, all simple tasks, so to speak. And then you turn up the complexity, and as you do it, the basis on which your work improves, and you can start developing spin-offs that you can actually use for solving practical applications. And those spin-offs will become more and more powerful with time because they're based on an ever stronger basis. So that's about it. Thank you for your attention.